All right, so let's go through some full-on examples here of solving a hypothesis test question for two proportions. So Sarah and Miranda were assigned to do a project on response bias for their AP Statistics class. They investigated whether the characteristics of the interviewer can affect the response to a survey question. At a local shopping center, they asked 60 shoppers the question, "Do you like tattoos?" When interviewing 30 of the shoppers, Sarah and Miranda wore long-sleeve tops that covered their tattoos. For the remaining shoppers, the interviewers wore tank tops that revealed their choice of tattoos. Excuse me. The choice of, and I see this phrase here, long sleeve or tank top was determined at random. Sarah and Miranda suspected more people would answer yes when their tattoos were visible. Set up and perform a hypothesis test at the 5% significance level to see if the proportion of people who said yes was larger when tattoos were visible. All right, so a couple of things going on in this problem. This problem is an experiment. We can tell that because there are two groups of people. There are the people who were asked the question when the girls are wearing a tank top, and there are the people who are asked the question when the girls are wearing the long sleeve. But the reason why it's an experiment is because that the girls decided who was in those groups. So like they flipped a coin or something, some sort of random technique, and then they decided how they were going to ask that question to put those in the groups. So the long sleeve and the tank top, those are our groups. Those are our treatment groups. So when we look at this, we have group 1 and group 2. Group 1 would be the tank top group. Those are when the tattoos are visible, and the long sleeve group would be the non-visible group. Okay, the other thing I noticed is it says that we're asking about people who said yes, which means that our category of interest, the one that we are counting, is the yes category instead of the no category. We do have both. So the two pieces of information we need from this table are the yeses and the totals. Those are our X's and our N's. So just be cautious if you're ever given data and they give you yes and no, but not total, you could still find it. Okay, or sometimes you're just given data that you don't need. So make sure you're sure which category you need here. All right, so for hypothesis testing, remember we use our acronym PHANTOMs. Okay, so our first, I gotta move my picture here. Our first thing we're going to do is we're going to define the parameter, P, define the parameter. Now we have two parameters here. You can do this in a couple of different ways. You could say something like P1 is the true proportion who would say yes when tattoos are visible. That's the tank top group. And P2 is the true proportion who would say yes when the tattoos are not visible. You could write it as a difference like we did with confidence intervals yesterday. Like P1 minus P2 would be the, I probably should say, the true difference in proportions of visible and not visible who would say yes, or something like that. Okay, so you don't have to do both of these, but I personally like the first one. So that would be how I would write this. And then I also want to point out this phrase, who would say yes. All right, so that's really important because we want to make sure we imply that we're not talking about the people who said yes, because the people who said yes, that's the 18 and the 11 in this problem. That's P hat. Okay, that's the sample proportion. Okay, that's the statistic. So we want to make sure we're implying that this is like if we went and did this again and we were able to talk to everybody. Okay, that'd be what we're kind of talking about here. Okay. All right, so there is my value there. Now, the next thing I want to do is I want to talk about the hypotheses, which apparently I have. Oh, there they are. So my PowerPoint is a little messed up, but that's okay. We'll get it fixed. So our hypotheses here, H for hypothesis, our null hypothesis is always a statement of equality here. So we're going to use our alternate hypothesis will be, it says the proportion was larger. So remember you want to look for that inequality word. So we're going to talk about a right-tailed test here. P1 is greater than P2 because P1 is the proportion of visible tattoos. And probably the reason why they think this would be true would be because if someone is standing there in front of you and they're covered in tattoos and they say, "Do you like tattoos?" A lot of people, if they didn't, they wouldn't want to say so because they don't want to be confrontational. Okay, so they might give a different answer. Okay, so when we do check this, remember we have to check those conditions for inference, which are random, 10%, approximately normal. So is this random assignment to two independent treatments because we're in an experiment? Yes, and we can tell that because it says in the problem prompt that this is determined at random. Okay, now since we are not taking a sample, then we don't have to worry about the 10% condition. And what you want to look out for this 10% condition is, remember, if you're sampling from a large population, you want to make sure you don't oversample from that population, because when you do, it really affects that standard deviation calculation accuracy, which some of our numbers are based on. So we want to make sure we're careful about that. That's one of the things we need for independence. So here we're not sampling because they did kind of talk to shoppers, but it doesn't say they like took every shopper and like interviewed every fifth one or anything. So it doesn't really imply that they have shoppers. These are people that exist. There's no implied that we're random here. We don't know if these are representative or not like that. So we're not really going to touch that. It doesn't really mention that we're doing random sampling. We know we have the random assignment, so we're just going to pretend like these are volunteers and go from there. What you want to look for in a case of sampling is like two distinct populations, like the shoppers at the mall and the shoppers at the food court, or like the shoppers in Avon versus the shoppers in Brownsburg. Like you have two groups and you pick from the two groups. These all came from the same group of shoppers. And so we had one group, and then we decided what groups, what subgroups to put those in, what treatments to put them in. Okay. Now the other thing that we need to check is that the sampling distribution is approximately normal. And remember, we're going to check that using these expected counts. The expected counts, though, since we are working in a hypothesis test, we do not know what the population proportions are. We're just going to assume, for the sake of this problem, that they are the same. So if we're trying to figure out the best guess for what these two numbers are, and instead of using the p-hat values individually, the best guess would be to use this p-hat combined. And remember, this is on your formula sheet, and it says on the formula sheet, if p1 equals p2, use this instead. So that's your responsibility to look at that formula sheet and go, okay, all right, this is a p1 equals p2 situation. This is a hypothesis test, which means that this is the number I'm going to use for all of my checks and all of my formulas, where I normally would just substitute in p-hat 1 or p-hat 2. All right, so this p-hat combined is the combined successes over the combined sizes of the groups, and we get 0.481. And so we're going to check N1 times this number, and N1 times 1 minus that number, which is 0.517. And then we'll take N2 times that number, and N2 times 1 minus that number. And you'll notice that it's like, I just wrote down the same thing twice. Okay, so my advice to you, again, is not to write these symbolically, because you don't want to accidentally mess it up and forget like a p-hat C or something and have the wrong notation, because they can score you down for that. So go ahead and show substitution into these, but you need to show each and every one. If you don't show them twice, it's not going to look like you checked both sample sizes. So it looks weird here because the two group sizes are the same. Okay, but don't stress out about that. I had someone ask in one class, they said, well, can we just write like both group sizes are the same, so these values would be the same for the second set of expected counts? Yeah, sure. But you could also just write the thing again, and that's a less writing and faster. So either way. All right, now both of those are greater than 10, which means we know our sampling distribution is approximately normal. So now we are ready to name that test. All right. And let me get back on my screen here. There we go. All right, so we have checked our assumptions and conditions, and now we are ready to name that test. Here we go. So this is a two-sample z-test for the difference in population proportions. Now that is its name. That's what you should write down on your paper. Okay. If you forget that word for difference of, you're probably not going to be scored down. If you say two-sample z-test for population proportions, you're probably going to be okay. But this is its name. And you might say, but we're not taking a difference. Look at our null hypothesis. But remember, this null hypothesis is basically the same thing as saying P1 minus P2 equals 0. Okay, so that is another way just to write that same null hypothesis. So we really are doing a test for a difference. We are doing a test for a difference because we're seeing, is there a difference? Is there not a difference? Okay. All right. So what you want to do next is you are going to want to run a two-proportion z-test in your calculator. So you are going to take your ti-nspire and you are going to go menu. Okay, so if you have your calculator, go ahead and pause and get that out and get that ready. You're going to go menu, you're going to go statistics, okay, you're going to go stat tests, which is at the bottom, okay, and so I think this keystroke is 6 and then 7, and then you are going to want number 6, which is the two proportion z-test. Okay, now in this two proportion z-test field in your ti-nspire, you are going to enter your x1, n1, x2, and n2, which are these numbers over here from the chart. Okay, and we want to pick in the drop-down menu the appropriate hypothesis, which is the greater than in this case. Okay, when you click OK, you're going to get this readout over to the side. So again, if you are doing this from home, go ahead and pause your video. Make sure you can do this in your calculator. And if you need help, then let me know. Okay. So we get our report back, and notice here are the two things that we need. Okay, we get our test statistic and our p-value. Test statistic and the p-value. So we're going to write those down. So remember, T stands for test statistic, and O is obtain the p-value. And we could do these by hand as well, but here they are from the ti-nspire. There's a test statistic, there's a p-value. Also, just notice over here, p-hat 1, that's what you get when you take 18 out of 30. P-hat 2, that's what you get when you take 11 out of 30. And then look where it just says p-hat. There's our p-hat combined that we use to check our sample counts. So if you're doing a problem like this and you like you'd get this in your calculator, what's that p-hat combined? Like, oh, what's that p-hat? That's p-hat combined. Oh, if you didn't use that to check your counts, then you should go back and fix what you did and use that number to check your counts, okay? Now, if we were going to do this by formula, we could, and you might need to do this for multiple choice questions. So you need to be prepared to do this. So if I want to find the test statistic, remember, standardized test statistic, Z, is going to be statistic minus parameter divided by standard error of the statistic. So our Z-score then, our statistic is the difference in sample proportions. So we're talking about the difference in the 18 out of 30 and the 11 out of 30. That's p-hat 1 minus p-hat 2. That's basically what you'd get if you took 0.6 minus 0.366 there, okay? And then our parameter is the difference in population proportions, which we already said, since we're doing a difference in population proportions test, P1 equals P2 means that P1 minus P2 would equal 0, so you just put 0 in there. Okay, and then for our standard error equation, remember that's P times 1 minus P over N, and you do that for both groups and add them together because we're adding the variance. We're going to use that p-hat combined number in that check. So the p-hat combined gets used for the sample count check and for this standard error. Okay, that's where that 1.808 comes from. And then if I wanted to find the probability then, that p-value, okay, I know that we're talking about a normal distribution. I have a test statistic over here of 1.808. And since we're testing a greater than test, I want that area in the right tail. So I would do a norm CDF. Menu, statistics, distributions, norm CDF number 2, from 1.08 up to infinity. Since it's a z-score, we go from 0 to 1, okay, and we end up with that same probability, that same p-value there of 0.035. That's the same thing that our calculator gave us. All right, so now let's do our make a decision here. So this p-value is 0.035. The problem tells us it's a 5% significance level. All right, so since it's a 5% significance level, we look at our p-value. Our p-value is less than or equal to alpha. P-value is low, reject the hoe. All right, so since the p-value is less than alpha, I reject the null hypothesis. There is convincing evidence that the proportion of people who say yes when tattoos are visible is greater than if they're not visible. So remember, we're going to make this statement about hoe, and then we're going to make this statement about ha. Statement about the null hypothesis, statement about the alternate hypothesis. But there's one other thing that it's not in my notes that you really need to add here. Okay, this is an experiment, which means we're allowed to say cause and effect. We think it was the shirts that made a difference in the way people responded. Yeah, we think that this evidence is strong enough that these shirts caused people to answer different. When they had their tattoos visible, we think that that treatment caused more people to say yes. Okay, so the cause and effect is there because we have the random assignment. But what we don't have is we don't have random sampling. And since we don't have random sampling, there's nothing in the problem that implies that they randomly selected these people from a general population of shoppers. Then we can't really generalize back to the population. We can't say this is true for everyone or for all people or for even all shoppers, really. Okay, so we want to tag on this sort of like weasel statement here that this is really just for people similar to those in our study. Not like for people in the study, because that's the p-hat values. So we don't want to refer to that. We don't want to say people who said yes. So we want to make sure we're talking about this is like for future. We're like trying to generalize this back. We're trying to make an inference to something. And the best we can do is to say for people like those in our study. Okay. All right. So one more example here. Okay. Move my thing again. Okay, researchers decided to study to compare the proportion of children who come to school without eating breakfast in 2 local elementary schools. A simple random sample of 80 students from school 1 found that 19 missed breakfast today. At school 2, a simple random sample of 150 students included 26 who missed breakfast that day. More than 1,500 students attend each school. Do these data give convincing evidence that the difference in the population of a difference at the population proportion at the 5% significance level? All right, so again, I see 2 groups here. This is definitely a 2-group problem. We've got kids at school 1 and we've got kids at school 2. And this is different from the last problem. This is definitely an observational study, not an experiment, because we didn't put kids at these schools. These kids were already at these schools. These kids are selected in place from 2 different populations. Okay, so this is an observational study. We're still going to do some comparisons here. Okay, so just kind of skimming through the problem, I see in school 1, we've got 80 and 19 as our counts, and school 2, we've got 150 and 26. So unlike the last one, we had 30 and 30. These 2 sample sizes are different. Okay, so here is my proportion. Okay, my population parameter. So I have for this one, I wrote it as a difference. P1 minus P2 is the true difference in the proportions of students at school 1 and school 2 who missed breakfast that day. Now, if you wanted to, you could also say P1 is the true proportion of students at school 1 who missed breakfast that day. P2 is the true proportion of students at school 2 who missed breakfast that day. That would also work. You don't have to necessarily write it as a difference. You can write as P1 equals and P2 equals. That's fine. In a confidence interval, we like to write it as a difference because at the end, that's exactly what we get is a difference. All right, so for our null hypothesis, remember we want to look for that inequality word, and the only inequality word we have in this problem is literally the word difference. Is there a difference? So the HO is going to be P1 equals P2, and our HA is going to be P1 is not equal to P2. And it did mention that our alpha, our significance level is 5%. Okay, so difference, we're going to say not equal to. So this is going to be a 2-tailed test. All right, so to check our assumptions for conditions, remember we went random, 10% approximately normal, 2 independent, that's assumed, and random, that's stated, samples. Okay, so we do have 2 random samples. We have an SRS and an SRS, and we're assuming that since we took these from 2 different schools, that they're independent, they're not talking like brothers and sisters attend different schools or something like that. Okay, now we are sampling. Sampling means we need to check the 10% condition, and fortunately for us, they tell us that more than 1,500 students attend each school. That's a really useful piece of information because we don't know anything about these schools. We don't know if they're like what kind of communities they're in. You know, I went to a little bitty elementary school that had 150 people in it, but my son goes to one that has over 800. So we're going to assume these are really, really big schools for the sake of the problem so that we can meet this 10% condition. So we're going to check that the sample size, 80 for school 1, is less than or equal to 10% of the entire population of school 1, which they said is at least 1,500. So I'm going to put 1,500 in there. 10% of 1,500 is 150, so this checks out. Same thing for school 2. We have 150, okay, is less than or equal to 10% of 1,500. That's 150, but they said more than 150, so this is really a number bigger, so we're good to go here. So unlike other times when we've checked the 10% condition, I don't have to say reasonable to assume here because like we actually have the number. We can just check. So it's not like they said of a very big school or of a university or something like that. Okay. The other thing we need to do is we need to check our expected counts to see if the sampling distribution is going to be approximately normal. Okay, and so remember, because we're in a hypothesis test, we have this assumption that P1 is equal to P2. We don't know what P1 and P2 are. If we know those, that's the best case thing to do to check these assumptions. Okay, but we don't, so we would normally use P hat, but we got 2 values of P hat coming from 2 populations that we're assuming are the same. So the best guess for P hat is going to be this P hat combined. And remember, that is on your formula sheet. And there's a statement that says if P1 equals P2, use this as your P hat value. Okay, so this is what we're going to use for the standard error formula. This is what we use in the expected counts formula. Okay, so P hat is the 19 plus 26 over the 880 plus 150. So we're talking about our successes, the kids who ate breakfast, who missed breakfast. Out of the total, we get 0.196. we're going to go through and check our n times p's. So for p1, we're going to check this count. And for p1, we're going to check the opposite, the 0.804, that complement count there, 1 minus p. We're going to do that again for 150. Notice that all of our expected counts are greater than 10, which tells us that our sampling distribution is going to be approximately normal, which is good because if it's approximately normal, that means when we find our z-score here in a few minutes, that probability is going to be accurate. Okay, so the name that test, this is a 2-sample z-test for the difference in population proportions. Now again, that's its name, that's what you should call it. But if you don't want to call it that, you could probably leave off that difference and they're probably not going to score you down. Okay, so here's that test. So I'm going to do this in my calculator. Now, again, we did this on the previous example. You're going to go Menu and Statistics. And you want to pick the one that's number 7 that's going to say stat tests. And then this guy right here is the one you want, which I believe is number 6, the 2 proportion z-test. And we're going to go ahead and put in our x1 and n1 and x2 and n2 from the problem. And our alternate hypothesis, we're going to choose not equal to. Okay, when you run this in your test, you are going to get the z-score for our sample difference, and you are going to get the p-value, which again is the probability of getting a test statistic like ours or more extreme, given that the null hypothesis is true. All right, so there is T and O, test statistic, and obtain the p-value. Okay, and now we're ready to make our decision. Oh, let's talk about how to do this by hand first. I forgot I had this on here. So the standardized test statistic, again, because we're doing a z-test, this is a z-score. Okay, so what we would expect is the difference in the statistic. The difference in statistic is that p-hat1 minus p-hat2. That's the 19 out of 80 and 26 out of 150. But the difference in the parameter is going to be 0 because we set them equal to each other. In our standard error formula, notice in the numerator where p-hat1 and p-hat2 are, we're just going to be using p-hat-c for both of those. So those numerators are the same. However, the denominators are different. That's giving me a z-score of 1.168. Okay, now what this would mean in terms of a picture, since we have a 2-tail test, I would want to find the probability that in one of the tails, so I would need that right tail there, for example, and so I would use my norm CDF option here. And for the norm CDF, I'd go from 1.16 up to infinity, and I would hit OK. And that gives me a norm CDF, that gives me this 0.121. Oh, sorry, I got my decimal place in the wrong place. 0.121 there. Okay, that's that probability right here. But because this was a not equal to's, it's a 2-tail test, which means I also want the area over here to the left of negative 1.168. Oh, my handwriting is terrible. So I have another 0.121 over here. So I'm going to take this, I'm going to multiply it by 2, and there is the actual p-value. Okay, so the p-value is double the area of the tail. Now, when you run the 2-tail test, it gives you that right number because it's doing that already for you. But if you are doing it by hand, that's a little thing you need to make sure you're paying attention to, is that you need the extreme. But if you're doing a 2-tail test, it's that double extreme. Okay, now I'm ready to make a decision. It says we're at the 5% significance level here. The p-value is definitely bigger than alpha. Oh, I shut down my computer. The p-value is definitely bigger than alpha, okay, at 5%. A lot of times on the AP exam, if they don't give you an alpha level, it's because the probability is enormous compared to whatever a reasonable alpha would be. All right, so since the p-value is greater than alpha, I fail to reject ho, fail to reject. So that means I'm not convinced of ha. Okay, so I'm not convinced that the true proportion of students at school 1 and school 2 who miss breakfast is different. I think that it's plausible they could be the same. I'm not going to say they're the same. Okay, so remember, you're going to always make this statement about ho, and you're going to make this statement about ha. You want it to be in context. Okay, all right. That is the last examples in the notes for this section. If you have questions, please let me know.